Late in the summer of 1977, an historic mission of exploration was launched. Twin spacecraft, christened Voyager 1 and 2, broke free from the Earth's gravity on journeys to the outer reaches of the solar system. Their primary destinations were the four giant outer planets: Jupiter, Saturn, Uranus, and Neptune. For 13 years, the Voyagers probed these mysterious worlds at close range, while collecting data and transmitting stunning images back to Earth. Among thousands of pictures of planets and moons, perhaps the most memorable was recorded on February the 14th, 1990, when Voyager 1 approached the edge of the solar system, then turned back toward the Sun. With its wide and narrow-angle cameras, the spacecraft captured unprecedented views of our home star and 6 of its orbiting planets. One of them appeared as a small pale dot, engulfed by a ray of sunlight. It was the Earth, from nearly 4 billion miles away. While the world gazed intently at this pinpoint of light, timeless questions about its meaning, purpose, and significance suddenly took on new relevance. And once again, as in ages past, we paused to consider our planet's role within the grand scheme of the universe. The mystery of the Earth's significance in the universe has challenged philosophy and science for more than 2,000 years. Early perceptions were shaped by the work of the Greek scholars Aristotle and Ptolemy. They taught that the Earth sat motionless in the center of the heavens while the moon, sun, and other stars and planets revolved around it. This geocentric view was the foundation of Western cosmology for 18 centuries. Then, in 1543, the Polish astronomer Nicholas Copernicus ignited a revolution. In his book on the revolutions of the heavenly spheres, Copernicus argued that the Earth was not stationary, but instead orbited with the other planets around the Sun. For the first time, a correct understanding of the mechanics and structure of the solar system was in sight.
The idea of the moving Earth seemed to violate some fundamental principle, but Copernicus somehow had the mental power to imagine what even to him seemed absurd. So he thought the impossible. The Earth moves. And once you imagine the Earth moving instead of the Sun, the mathematics of that cosmic machine started to make sense. It was the key that unlocked one of the great mysteries of the universe.
Copernicus had laid the cornerstone for modern astronomy. Yet, 400 years after his discovery, the empirical fact that our planet was not the center of the solar system had evolved into what is now known as the Copernican principle. The idea that the Earth occupies no preferred place in the universe.
Copernicus had a theoretical way of explaining the apparent motion of the planets across the sky. That's all it was. It wasn't a theory that told us whether or not Earth was special, or whether we played some importance in the scheme of things, or whether every place in the universe was the same as every other place. Nevertheless, this reinterpretation of Copernicus became prominent in the 20th century. It's often called the principle of mediocrity. This principle says that our location and our status are mediocre, they're unexceptional. As a result, we should not assume that we are in any way privileged or that the universe was designed with us or beings like us in mind.
The Copernican principle and the concept of the Earth's insignificance was popularized during the 1970s and 80s by the late astronomer Carl Sagan. In his best-selling book, Pale Blue Dot, Sagan wrote,
"Because of the reflection of sunlight, the Earth seems to be sitting in a beam of light, as if there was some special significance to this small world. But it's just an accident of geometry and optics. Look again at that dot. That's here. That's home. That's us. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark."
One reason for the widespread acceptance of the Copernican principle can be traced to a discovery made on this mountaintop overlooking Los Angeles. Between 1921 and 1926, the astronomer Edwin Hubble used this telescope to make some of the most important discoveries in the history of science. Through the window of the Mount Wilson Observatory, Hubble unveiled the true magnitude of the universe.
At the time that Hubble was doing his work, many astronomers believed that the galaxy, our galaxy, marked the edge of the universe, and there was nothing beyond it.
Edwin Hubble altered this perception of the universe when he used the most powerful telescope of his day to photograph indistinct objects in space. Long thought to be nearby clouds of gas and dust, Hubble determined that these patches of light were actually individual galaxies, many as large or larger than our own Milky Way.
The implication in what he found was that the universe consists of, indeed, billions of galaxies, each with many billions of stars and planets. And it was a universe with a wealth of numbers and variety that transcended the imagination of both layman and astronomer. He, in effect, enlarged the boundaries of the universe.
Edwin Hubble revealed that the Milky Way galaxy, encompassing more than 100 billion stars, including our sun, was a mere pinpoint of light in the universe.
When Hubble found that there were many galaxies, we saw that our galaxy was nothing distinguished at all, just one ordinary galaxy.